Welcome to my channel, InnovaWorld. Today, I will solve a problem based on aircraft performance and flight dynamics. If you are new to this channel, mostly we make videos on aerospace related tips and tricks to crack competitive examination and also career guidance videos for aerospace and aeronautical engineers. To know more about other videos, link is in the description box. However, stay tuned to our channel and website to lead the better future like jobs, internship, training and many more. Let's proceed for today's topic. First question. For conventional airplanes, which one of the following is true regarding roll control derivative and yaw control derivative, where del R is radar deflection? They have given 4 options. First one is when the roll control derivative is greater than 0 and yaw control derivative is less than 0. Option B, roll control derivative is less than 0 and yaw control derivative is greater than 0. C option, roll control derivative is less than 0 and also yaw control derivative is also less than 0. And the D option is roll control derivative is greater than 0 and yaw control derivative is greater than 0. Let's see the solution. Simply we can follow strip theory, which says that the roll control derivative of a wing which can be written like a positive, whereas yaw control derivative, it is just an analogous to each other. So they have given the formula, that is yaw control derivative we get as negative of CD naught by 4. Roll control derivative, it is a positive value. So from this value we can choose the right option is A. Velocity of an airplane in a body fixed axis is given as 100 minus 10 20 meter per second. The side slip angle is need to find degrees, round off to 2 decimal places. This question consists of 2 marks and no negative marks. Let's see the solution. These are the given data, that is a velocity. Now U is 100 meter per second. V direction we have the negative 10 meter per second and W is 20 meter per second. Now we need to find the side slip. Now what is side slip angle? Is the angle between the velocity vector to the plane of symmetry. Mathematically we can write like beta equals to sine inverse of V by the magnitude of the V. So what does it mean by magnitude of the V? Can be written that the root over of U square plus V square plus W square. Now when we substitute that to this magnitude of the velocity, we get that 100 square plus 10 square plus 20 square we get as 102.47 meter per second. Now simply substituting the values in the formula, that is beta equals to sine inverse of minus 10 divided by 102.47, we get beta value is around minus 5.60. Based on the answer key given, which should be range within minus 5.57 to minus 5.62, which is within the perfect limit. So here the minus sign is very important and where we have achieved it. The eigenvalues for Fugit mode of a general aviation airplane at a stable cruise flight condition at low level angle of attack are lambda 12 equals to minus 0.02 plus and minus I 0.25 if the acceleration due to gravity is 9.8 meter per second square. The equilibrium speed of the airplane is need to find in meter per second and round off to 2 decimal places. This question is also carries 2 marks and no negative marks. Let's see the solution and we'll see the given data first, that is lambda, that is characteristic values, that is minus 0.02 plus and minus 0.25 of I. So from there we can segregate the real value, that is real eigenvalue, and the imaginary eigenvalue. Imaginary eigenvalue lambda I and the real eigenvalue is lambda R. To find the Fugit speed of an aircraft velocity, recall the formula for the Fugit velocity. So V Fugit equals to root over 2 into G by damping frequency. G is given, which is unknown is omega n. Now recalling again, the damping frequency becomes minus real factor of eigenvalue divided by the damping ratio. So again from here lambda r is known to us, but we don't know the damping ratio. Again the formula of damping ratio, that is a relation between the real eigenvalue and the imaginary eigenvalue. So damping ratio can be written as root over lambda r square by lambda r square plus lambda I square. So by substituting the values of lambda r and lambda I, we can find the damping ratio about 0.0797. Now substituting back, we get that omega n value is around 0.251. So substituting back that respective value into the Fugit velocity, Fugit speed of the airplane, root over 2g omega n. So g is 9.81 and omega n is 0.251. Substituting the values, we get 55.27 meter per second. Round off to 2 decimal places. Answer ranges from 55.25 to 55.65, which is within the proper limit. For 3 different airplanes A, B and C, the yawing movement coefficient Cn was measured in wind tunnel for 3 settings of side slip angle beta and tabulated as shown in figure. Which of the following statements is true regarding the directional static stability of the airplane A, B and C? Option A, B and C are stable. B, only airplane C is stable, both A and B are unstable. C, airplane C is unstable, A and B are stable, with A being more stable than B. D option, airplane C is unstable, A and B are both stable, with A less stable than B. Let's see the solution. So here are the given parameters. Now based on the directional stability, it is been known that when Cn beta is greater than 0, it is stable, and when it is less than 0, it is unstable. So first we will plot a graph between the Cn versus beta based on the graph. When the curve is positive, it is stable, and when it is negative, or when it is curve is negative, it is unstable. So we can clearly state from this graph that option C is a right option, that airplane C is unstable and A, B both are stable, with A being more stable than B. For a general aviation airplane with tail efficiency eta equals to 0.95, horizontal tail volume ratio VH equals to 0.453, downwash angle slope d epsilon by d alpha equals to 0.35, wing lift curve slope 4.8 radian inverse, horizontal tail lift curve slope 4.4 radian inverse, shift in neutral point location as a percentage of mean aerodynamic chord is need to find out in round off to 2 decimal places. So let's first write down the given data. First they have given eta, that is tail efficiency 0.95. Then coming to the next is a tail volume VH, that is 0.453. Then downwash slope d epsilon by d alpha 0.35. Then comes the wing lift curve slope dCLW by d alpha equals to 4.8 radian inverse. Then horizontal tail lift curve slope is about dCLT by d alpha is 4.4 radian inverse. And we need to find is a shift in neutral point location as a percentage of mean aerodynamic chord. Now from here it is clearly been stated that what we need is that the static margin. Static margin is simply the distance between the neutral point and the actual center of gravity. So first of all here we need to find the static margin. So first let's recall the formula for the static margin, that is x bar NP, that is neutral point, minus x bar of AC, that is aerodynamic center, divided by the chord, equals to eta VH CL alpha T by CL alpha W 1 minus d epsilon by d alpha minus Cm alpha F by Cm alpha W. Since they have not given any such value for the fuselage, we can simply ignore that respective value. Now what is a CL alpha T, C and CL alpha W? CL alpha W means dou CLW by dou alpha, and CL alpha T means dou CLT by dou alpha. That is a lift curve slope for wing and the tail. Now we can simply recall the formula, that is after cancelling of the fuselage we get SM, that is a static margin, equals to eta VH CL alpha T by CL alpha W 1 minus d epsilon by d alpha. Now simply substituting the respective value, eta is 0.95 and VH is on 0.453, CL alpha T is 4.4 and CL alpha W is 4.8, and 1 minus of dou eta by dou alpha is 0.35. So after that we get equals to, after solving this above equation, we get 0.2564. So in terms of percentage, so when we need to convert in terms of percentage, we get as 25.64 in round off to 2 decimal places, and based on the answer ranges from 25.60 to 25.70, which is within the proper limit. A single engine propeller driven general aviation airplane is flying in cruise at sea level condition. Density of air at sea level is 1.225 kg per meter cube, with speed to cover maximum range. For drag coefficient, CD equals to 0.025 plus 0.049 CL square, and wing loading W by S equals to 9844 Newton per meter square. The speed of the airplane is need to find meter per second and round off to 1 decimal place. Now first we'll see the solution and the given data. In the given data, first they have given is the density, that is 1.225 kg per meter cube, CD, that is a drag coefficient. They have given the equation 0.025 plus 0.0049 CL square. From there as we know from the drag polar equation, CD equals to CD naught plus K CL square. We can segregate the CD naught becomes 0.025 and K represents 0.049. And from there wing loading, it's around 9844 Newton per meter square. We need to find the speed of the airplane. Now based on the question they have given, that is a maximum range. So first we'll go with the steady state condition, that is lift is equals to weight, and we know lift means half rho V square SCL equals to weight, and by rearranging we get that V equals to root over 2 W by S by rho CL. Now all the values are known, that is W by S, which is 9844, and rho is 1.225 and CL is unknown. Now based on the maximum range, that condition, that is minimum drag condition. So based on the minimum drag condition, that CD naught equals to K CL square. So based on that, CL becomes root over CD naught by K. So from here we can find the value of CL becomes 0.7143. So after that, substituting the value back to the original formula, that is CL value, and we get around V equals to 150.0006. So we can simply write in 2 decimal place at 150.00 meter per second, and as per the answer key given is that 149.0 to 151.0, and which is the proper limit. Hope this solution was very helpful for you all. Don't hesitate to ask queries either in comment box or drop a mail. Subscribe and hit the bell icon to get further notifications. Thank you for watching the video and fly high.